All right, so here we go. We're doing another one for thin films. So this time we have sort of the exception to the rules with IB in terms of the thin films. This is actually a really cool thin film that a lot of you have in your daily life. So this is like if you pay extra for nice glasses, for reading glasses, or just your regular eyeglasses, you'll have paid for this extra film on the glasses, and when you look at these, you'll see this sort of purpley reflection, this sort of sheen that they have. And we're going to understand why that happens, and it's totally related to thin films. And let's make sure that we understand that what we have here is we have glass. So the glass itself, which is really thick, this is a zoomed in picture. We're looking just on the very outside edge of that glass, has this very thin coating, and it can be just a few atoms thick. This is a very, very thin coating. In any case, the index of refraction of the glass here is 1.52, the air is 1, and then the coating will be somewhere in between. So this time the coating we're saying is 1.38 for an index of refraction. So the first thing you're going to notice is that both the light coming in, we have white light coming in, so the light here on reflection will have a phase shift because it's in a small index of refraction bouncing off of a big index of refraction. Means it's a closed reflection. It will have a 180-degree phase shift. And so this light right here goes through a whole half of a wavelength of change right there, or a pi phase, we say sometimes. But in any case, it also happens down here because the light that goes through, and there's no phase shift as it goes through. So it goes through, and then this one is going to bounce as a closed reflection also because you can see 1.52 is bigger than 1.38. So you get a phase shift here as well. So you're getting phase shifts at both places. And so this light that's coming out is going to be out of phase from each other, only dependent on the delta L in the film, because they both had the same amount of shift at reflections. Okay, so this is not the situation that your standard IB equations are made for. So you have to adapt the IB equations, and you're gonna switch constructive and destructive because of the phase shift differences. Okay, this says find the smallest thickness of the film that will give destructive interference for the green light that's in the middle of the visible light. So what's the whole point here? The point is to put a thin film on the glass so that the white light that's coming to your eyeglasses go right on through to your eye, because it'll go through the coating, then through the glass, through the lens, and then eventually down and into your eyeball. So we want this reflection here to be destructive for green, because green's right in the middle of the rainbow of colors, right? So we'll pick 550 to be that destructive wavelength, and that 550 is out here in the air. And you could attack this with the IB equations, but I'm just going to common sense it again. If you really understand this idea, you're going to answer the questions more correctly, I think, in terms of they typically ask for explain why this is happening, where are the phase shifts, and this kind of thing. It's the wavelength in the film that actually determines what happens. So my first thing to do would be to take 550 divided by 1.38 and get the wavelengths that we're expecting to get. So that wavelength, whatever it is in there, is going to be, if the smallest coating that we're going to have here is going to make it be destructive, then I want to add a half of a wavelength when I go over and back, which is to say that the thickness will need to be a quarter of a wavelength. So that's kind of cool. So I'll just scroll just enough so you can see that. So when we take the 550 divided by the 1.38, we should get around 400. And what we do here is recognize that that's the wavelength of the light that will get destructively interfered. And so destructive interference will occur because we're half of a wavelength out. And so why do we divide by 4? The thin film will be 1/4 of that number because we need half of a wavelength. So a quarter of a wavelength going over, a quarter of a wavelength coming back means that this one that's on the right a little bit will be off by half of a wavelength of this one. They both shifted by a half on reflection, so they would still be the same unless there was a difference in delta L. And this difference in delta L, which is D over and D back, gives us why we're needing to divide by 4. So we end up with 100 nanometers. That is a very, very thin film. And so it's just a few atoms thick. And let's keep going with the question then. Explain why the light that you see from a film like this looks purple. So if we were to ask instead, well, okay, so the green gets blocked out, it doesn't reflect. What colors actually would reflect? And it would be on the other edges, like near the purple and over near the red. And that combined color gives it this particular distinctive sheen color that you see. It's actually a combination of colors that are the colors that, instead of being destructive, were actually constructive. And then C, where did the green light go? The green light, since it didn't reflect, because we had destructive interference on the reflection, the green light went on through. And that's the whole point. So the visible spectrum around the green, which is what you're trying to see with your eyeballs, goes through the glasses, and your glasses are not blocking any light. They're nice and clear and clean because they didn't break any light. One thing while I'm thinking of it, I wanted to mention, these pictures are always drawn with this coming in at a little bit of an angle. And that's just so that you can tell that there's reflection here, right? You want to be able to see that when I draw this picture, that there was this one, and then there was also this one. But now they're actually separated in space, which is not what we're talking about. We're talking about light that goes straight in, one reflects, the other goes through, hits the other side, comes back, and comes right on top of the other one. So they're not actually side by side like this. They're actually right on top of each other. And it's actually a much more complicated question to talk about light coming at an angle that then interferes with a different beam that was coming at a different angle that reflected on the surface instead of the one that went through. You can imagine if it actually was at this angle, the one that was going to interfere would be actually white light that was right alongside parallel, went in, reflected, and then came right back on top of this one, right? And in fact, if it's at an angle, the equations to figure out what's happening will involve tangents of this angle and sines, and it's a very interesting derivation that's not in the IB curriculum any longer, so you don't have to learn it. But in any case, we draw this sort of at an angle, even though we're really talking about it coming straight in. Okay. What if all of this, like doing it in your head, understanding the problem, you just want to check it with the IB equations? Like, that's also something you should be able to do. So let's take a look. If you look at the actual IB questions, which is what they're giving here, they're wrong. And they're wrong because these IB equations, remember, are assuming that we have phase shift at one, but not at the other. And since we're having phase shift at both, that means that these equations here are toggled. In other words, just change the word destructive and constructive, switch them over back and forth, so that this one is the one that you would use for constructive, and this is the one that you would use for destructive. So we want destructive, but because of the phase shifting happening at both, we're going to use this equation for destructive instead. Okay, and then let's see what happens. So we have the wavelength in the air was 550. We have the index of refraction in the coating of 1.38. And let's just see how that works out. So we're looking at this, and we're using this one for destructive instead of constructive, as I've explained. So for this lambda, there's going to be 550. For m, you're going to put 0 because they asked for the smallest film possible. And if this m is bigger, then obviously d will get bigger. So we want the smallest d. And remember, with this equation, m can be 0. With this equation, m starts at 1. But with this equation, m starts at 0. So anyway, this is 0. We're trying to solve for d. We're going to divide by n. Notice in my mind, that's the 1.38, and we have the 550 divided by the 1.38. That's how we had that other wavelength in the first place. But here we're just chugging without thinking. So you put m is 0, 550 for lambda, 1.38 for n. D is what we're trying to solve, and you divide by 2. So you'll notice we end up dividing by 4 totally because there's this half, and we also have this other 2 coming in. And so we get the 100 nanometers that we were expecting to get. So that's pretty awesome. Finally, I'm just going to say, this does a very nice job of explaining everything, and I'm not just going to read to you, but I would look carefully at this and make sure these sentences are making sense to you and why this happens. And hopefully this gives you just a little more clarity and mastery of what you're going to do with thin films on the IB exams. So that's about it for thin films for us. And I hope you're ready for some assessments on thin films at this point. Good luck, everybody.